Welcome to our lecture on ordinary differential equations. Today we are going to explore a fascinating and crucial concept known as equilibrium points. Understanding these points allows us to predict the long-term behavior of complex systems, from cooling coffee to growing populations, without even having to fully solve the underlying differential equations. Let us dive in and build our understanding from the ground up. To understand what an equilibrium point is, imagine you are holding a perfectly smooth marble. If you place it exactly at the very bottom of a round cereal bowl and let go, it just sits there, completely motionless. The forces acting on it are perfectly balanced. Now, imagine carefully balancing that same marble on the very top of a smooth, upside-down bowl. If you get it exactly right, it will sit perfectly still too. In both situations, the marble is in a state of rest, where nothing is changing over time. In differential equations, we call these special states equilibrium points. Once a system reaches one, it stays there forever unless an outside force pushes it away. Now that we have a physical intuition, let us look at the mathematics. An ordinary differential equation describes how a variable changes over time. This is usually written as a derivative. The expression on the right side of the equation tells us the exact rate of that change based on the current state. An equilibrium point is defined as a specific, constant value where this rate of change is exactly zero. When the rate of change is zero, the variable is no longer increasing or decreasing. The system is completely frozen in time. Simply put, it is a solution to the equation where nothing happens anymore. This brings us to the mathematical formula. We start with a general first-order differential equation written as dy by dt equals f of y. Here, y represents the state of our system, like a population or temperature. The variable t represents time. The derivative dy by dt measures exactly how fast y is changing, and f of y is the mathematical rule that calculates the speed. To find the equilibrium points, we introduce a special fixed value called y star. We set the function f of y star equal to 0 because we are looking for the exact moments when the system stops changing completely. Solving this algebraic equation reveals our equilibrium points. Before we move on, let us see this with a concrete example. Suppose a hot cup of coffee is cooling down in a room. The temperature of the coffee, T, changes according to Newton's law of cooling. This is given by the equation dt by dt equals negative k times the quantity T minus 70. Here, k is a positive constant representing the cooling rate, and 70 is the room temperature. The negative sign shows that the temperature is dropping over time. We want to find the equilibrium point of this specific system, which will tell us the final resting temperature of the coffee. To find the equilibrium point, we need to find the temperature T where the coffee completely stops cooling. This happens when the rate of change, dt by dt, is exactly 0. In this crucial step, we replace the derivative with the number 0. This mathematical substitution represents the physical state where the temperature is absolutely no longer changing. We are essentially asking the equation to tell us what conditions make the cooling process stop entirely. The right side of the equation remains exactly the same for now. Now we solve for the temperature. Since k is a known positive constant, we can safely divide both sides of the equation by negative k. 0 divided by any non-zero number is still exactly 0, which greatly simplifies our equation. We are left with 0 equals t minus 70. Finally, we add 70 to both sides to completely isolate t. This gives us our calculated equilibrium point of 70. Physically, this means the coffee will stop changing temperature exactly when it reaches 70 degrees, perfectly matching the room temperature. It will stay there forever. Let us look at a slightly more complex scenario. Imagine a population of fish in a lake, represented by the variable p. The growth of the fish population is modeled by the logistic equation dp by dt equals 0.5p times the quantity 100 minus p. The first part represents the fish reproducing. The second part, in parentheses, represents the limited food and space in the lake. As the population gets closer to 100, this part shrinks, slowing down the overall growth rate. We need to find all the equilibrium points where the number of fish remains perfectly stable. Just like in the previous example, an equilibrium point occurs when the population stops changing entirely. We set the derivative to 0 to find the exact moments where births perfectly balance out deaths. This leaves us with a quadratic equation to solve. To make the math easier, we divide both sides of the equation by the constant 0.5. This simplifies our equation without changing the fundamental relationship. Now, we are left with two distinct mathematical factors multiplied together that must equal 0, p and 100 minus p. According to the fundamental rules of algebra, if two things multiply to make 0, at least one of those individual things must be 0. We obtain our very first solution by setting the first factor directly to 0, giving us p equals 0. Physically, this represents a completely empty lake. If there are exactly 0 fish in the lake, the population will never change. It will stay at 0 forever because there are simply no fish present to reproduce and create more fish. But we have a second factor to consider. To find our next possible solution, we set the second factor equal to 0. This gives us 100 minus p equals 0. This represents a completely different physical scenario, where limited resources perfectly balance the natural reproduction rate. By adding the variable p to both sides, we find our second equilibrium point, p equals 100. This means if the lake has exactly 100 fish, the population will stay at exactly 100 fish forever. The system has reached a perfect sustainable balance. Now that we have calculated these points, let us visualize them using a tool called a phase line. The horizontal line represents the population size. The dots at 0 and 100 are the equilibrium points we just found, where the system is at rest. The arrows show what happens if the population starts near these points. Notice that arrows point toward 100, meaning the population naturally moves toward this balance. We call this a stable equilibrium. Conversely, arrows point away from 0, meaning any slight addition of fish causes the population to grow rapidly away from 0. We call this an unstable equilibrium. This diagram perfectly illustrates the difference between stable and unstable equilibria. A stable equilibrium is like the marble resting safely at the bottom of a bowl. If you nudge it, it naturally rolls back to the bottom. In our fish example, the population naturally stabilizes at 100. An unstable equilibrium is like a marble balanced precariously on top of a hill. Any slight disturbance causes it to roll away forever. Understanding these points is absolutely crucial. It allows engineers to ensure airplanes fly steadily and biologists to determine the maximum sustainable yield of a fishery without overfishing. To wrap up, let us review the key takeaways. An equilibrium point is a specific state where a system's rate of change is exactly 0, meaning the system remains constant over time. We find these points by setting the derivative in our differential equation to 0 and solving for the variable. These points act as the anchors of a mathematical model. They show us where a system will ultimately settle down, allowing us to predict long-term behavior without solving the full equation. You now have the foundational tools to analyze complex systems across physics, biology, and economics. Great job!